In this new lecture, we are going to talk about the numerical problems on electrical analogy concept. You might be able to recall that in the last few lectures, we were continuously discussing about the one-dimensional conduction problem without internal heat generation. This problem can be effectively solved by using the concept of electrical analogy. So we have got introduced to the concept of electrical analogy, and we have seen how the thermal resistances can be calculated for a plane wall, for a hollow cylinder, and for the hollow sphere. And then we have successfully extended this analogy for the resistances in series and resistances in parallel. Now we are in a position to find out the equivalent thermal resistance for the complex situations. Now in this lecture we'll be talking about. Thus, I'll go for some introduction. Then we'll solve three numerical problems. One is from composite plane wall. Second one is from composite cylinder, and third one is from composite sphere. So I tried to cover all the parts of your requirement of the variety of the problems. And my suggestion would be just don't see this video as it is. Just try to solve the problem before my solution. So what I'm doing, I'm just putting in the first slide the problem and with some basic idea about the problem. You just freeze your video over there, try to solve the problem at your own, and then see the next subsequent part of my video to get the solution and to cross check your answer. So this would give you a better idea for solution of the problem. Don't just follow my solutions. This is my humble request to all of you. Let us start. I'm Nitin Bhirud, working as associate professor in Sandeep Institute of Engineering and Management. And let us start with the first problem. A composite plane wall. Uh, Let me read the problem. The inside surface of brick wall conductivity is 1 watt per meter Kelvin of 10 centimeter thickness is at a temperature of 930 degrees Celsius. So we got a brick wall whose thickness is 10 centimeter, conductivity value is given, and the inside temperature is 930 degrees Celsius. And the outside surface is exposed to ambient air at 30 degrees Celsius, providing heat transfer coefficient of 20 watt per meter square Kelvin. The information itself indicates that the outside of the wall is subjected to convection because it is in contact with ambient air at 30 degrees Celsius, and there is a heat transfer coefficient of 20 watt per meter square Kelvin. The data itself indicates that there is convection at the outside surface. And in between inside surface to outside surface, the brick wall is there. It means that the mode of heat transfer through the brick wall is going to be conduction, and it will be followed by convection at the outer surface. Now what we are expected to calculate? Calculate the temperature of outside surface. What is the temperature of the outside surface? Also calculate, there is another condition, also calculate the thickness of the insulation. If at all the wall is insulated with a insulation having thermal conductivity 0.1 watt per meter Kelvin, that is needed in order to keep the outside surface temperature of surface temperature exposed to air not more than 90 degrees Celsius. So in the first part, you have to calculate the outside surface temperature. In the second part, we have to take that outside surface temperature as 90 degrees Celsius. But with the condition that there is an additional resistance, and that resistance will be provided by the insulation. So we need to draw the schematic diagram, to write down the given things, and then we can. Now at this point of time, once again, I'd like to remind you, just stop, pause the video, try to solve your problem. If you can solve it and just solve that problem as it was discussed in the previous lectures also, you have got already the methodology of solving the problem. Let me once again revise it for you, how to solve such type of problem. First step would be to write down the given things. Second step would be to write down the things which are expected to be calculated. Third thing would be the schematic diagram. In this case, we need to draw two schematics, one without the insulation, other with the insulation. Third, as we are solving the composite plane wall problem for one-dimensional steady-state conduction, electrical analogy is applicable. So whatever schematic you have drawn, you have to convert it into equivalent electrical network. And already I told you how many resistances are going to be there. So you can use that information for finding out the schematic diagram. Now mark the point on the schematic diagram, calculate the individual resistances, and then we can find out the required things. So these are the guidelines which are to be followed. I request you once again, don't follow the video right now. Just pause it and then find out the solution and check it with me. Thank you. So what is given to us is a brick wall having thermal conductivity 1 watt per meter Kelvin. Thickness is 0.1 meter. I'm converting it into meter. Uh, Inside temperature, I'm calling it as Ti, 930 degrees Celsius. Fluid temperature is 30 degrees Celsius, and H is 20 watt per meter square Kelvin. So, what are the assumptions in this problem? Already we know that it is going to be a one-dimensional steady-state conduction. We are going to assume all these properties of the object are going to remain constant. They are not going to change, particularly the conductivity value, because we know that conductivity may vary with respect to temperature. But here we are going to treat it as a constant. So there is no internal heat generation. The temperature, the value of H and the fluid temperature is going to remain constant and uniform over the entire surface of the brick, and there is no contact resistance when the insulation is applied. So with these assumptions, we can proceed. And what we are expected to calculate? In the first case, we are expected to calculate the outside temperature of the wall, and the second case, if the outside temperature is to be kept at 90 degrees Celsius, what should be the thickness of insulation if the conductivity value of that insulation is 0.1 watt per meter Kelvin. So this simple things we have to calculate. So let us start. So without insulation, I can draw the schematic like this. You can see that inside surface temperature is 930 degrees Celsius. There is brick which thickness is given, conductivity is given, some heat is flowing through this, and ambient air is exposed on the other side where temperature is T infinity 30 degrees Celsius. Heat transfer coefficient is 20 watt per. This is small h, 20 watt per meter square Kelvin, and I'm just converting it into how to convert this. Let me give you an important guideline. You have to always start with the highest temperature in the circuit. Now in this case, highest temperature is 930 degrees Celsius. Now from this highest temperature, the heat will flow through the brick. So what is the mode of heat transfer through the brick? It is going to be conduction. So the brick will offer one resistance for the conduction, and that's why there is one resistance. Then after the brick will reach to certain temperature, let us call this temperature which is unknown to us, which is to be calculated as TO. Then the outside surface. At the outside surface, what is there? There is a fluid whose temperature is 30 degrees Celsius. So what is the mode of heat transfer from the outside surface to the ambient air? It is going to be convection. So additional resistance is there in the circuit, and that is convection. Now whether they are in series or parallel, how to come to know? Because as we know, when we are going to take them in series, when the rate of heat transfer through both the resistances is same, and it is same in this case. If there are two paths or multiple paths for the heat to flow, then we are taking those resistances in parallel. There are no multiple paths in this case, so we can take them in series. So this is how we can draw the circuit. Next time onwards, I'm not going to give the details. I'll directly give you the circuit, and you should understand how I have drawn it. Using the electric analogy, what we can say, that is the rate of heat transfer is Ti minus To, that is Ti minus To delta T. I am using it for the first resistance divided by the brick resistance, that is T upon K. Same electric analogy can be extended, that is To minus T infinity upon 1 upon Ha. So I am using the second resistance now. So what is unknown? Now Q is also not known to us, but I need not to calculate Q because I am interested in finding out the value of To. If I substitute these values here, only unknown in this equation is TO, and if I solve it for TO, I'll get the value of TO equal to 330 degree Celsius. So this is my first calculation. Second calculation is to be done with the insulation. So I'm just adding an insulation, showing the insulation whose thickness is unknown now. We don't know the thickness of insulation, and the temperature of the outside surface is now known, and it is 90 degrees Celsius. So I have just drawn this electric schematic followed by the electrical network, starting with the highest temperature to the lowest temperature, identifying the different modes of heat transfer. Now here, additionally, I got the insulation. So insulation is the mode of heat transfer through the insulation is due to conduction, and this insulation will provide some heat resistance for the heat to flow, and that resistance is going to once again in series with the other previous two resistances. So now you might have noticed that TO is now after the insulation, outside surface of the insulation, that is equal to 90 degrees Celsius. So once again we can use this same electrical analogy. Now what I have done, I am using this electrical analogy for first two resistances Ti minus To, this Ti minus To, and they are in the bottom in the denominator. I got addition of these two resistances, that is R for brick and R for insulation. Okay, both are conduction resistance, can be calculated by T upon K, T upon K. Only the K and T are different. Okay, this T of insulation is not known to us, we need to calculate it, and then I'm equating it with the convective part, that is To minus T infinity divided by the convective resistance. So if I've just put the values in this equation, you can see I'm just putting 930 minus 90 in the numerator, 90 minus, and this T is 0.1 conductivity into area, and this area can be, in this case area is not specified, so we can take it at 1 meter square, and we can calculate for 1 meter square area, and we, if you do it, we can calculate the thickness of insulation is equal to 0.06 meter, and that is equal to 6 centimeter. So if you put 6 centimeter thick insulation of having thermal conductivity zero point 0.1 watt per meter Kelvin, then we can keep the temperature of outside surface up to 90 degrees Celsius. So that is the outcome from this problem. So this was our first problem. Let's go for the second one. Sorry. Uh, Problem number 2 is from composite cylinder, a thick wall tube of stainless steel. Thick wall tube of stainless steel, thermal conductivity of steel is 19 with 2 centimeter inner diameter. Inner diameter is 2 centimeter and 4 centimeter outer diameter. You can imagine the tube, 2 centimeter inner diameter and 4 centimeter outer diameter, is covered with a 3 centimeter layer, 3 centimeter thick layer of asbestos insulation with thermal conductivity of 0.2 watt per meter Kelvin. If the inside wall temperature, now just pay attention to this data is very important. Inside wall temperature of the pipe is 600 degrees Celsius. Inside wall means at radius or at this diameter 2 centimeter or radius 1 centimeter. What is the temperature? It is 600. And outside wall temperature is 100 degrees Celsius. Outside wall temperature of asbestos means the outer layer. So asbestos insulation is having thickness of 3 centimeter on this 4 centimeter outer diameter. Okay, and temperature of that layer is 100 degrees Celsius. Calculate the heat loss per meter length. Also calculate the tube insulation interface temperature. The interface temperature between tube and insulation, that we have to calculate. So you can pause, you can solve, and you can check your answer with me. So let me continue. The schematic is like this. The inner diameter, inner radius is R1, which is corresponding to 2 centimeter inner diameter. Outer radius of the pipe is R2, which is corresponding to 4 centimeter outer diameter, and outside radius of the insulation is say R3. So we can calculate the values of R1, R2 and R3 simply by converting these into meters, and then the first layer is of in between this temperature 600 to 100. The first resistance will be offered by the stainless steel and second resistance will be offered by the insulation. So there are two resistances, both are for conduction. First is conduction for the what you call steel, and the second one is conduction by the asbestos insulation. Only thing is that instead of using the equation T upon K or B upon K or L upon Ka, which was for plane wall, now we are using the thermal resistance for cylindrical system, which is natural log of R2 upon R1 divided by 2 pi K. It will become natural log of R3 upon R2 upon 2 pi K of asbestos into L for the second resistance. So if you add all these things, and the inner radius is 0.01, outer radius is 0.02, outer radius of the asbestos layer is going to be 5 centimeter, and it is can be calculated 0.05 meter, and the thick the conductivity values of both the materials are given to us. The inside temperature is 600 and outside temperature is 100. So if you use this logic and if you Of course, the assumptions, similar assumptions: one-dimensional conduction, constant properties, no heat generation, uniform heat transfer coefficient, constant T infinity, no contact resistance. Although the assumptions are same, it is suggested that all the time whenever we are solving the problem, we should write down the assumptions. That gives us a clear-cut idea about what we are supposed to do and how we are going to solve the problem. Although these problems are appear to be very simple, but if you follow this procedure of solving the problem, you can solve any type of real life problem, because real life problems may not come with this type of specific statements. So that they may have some vague information, some hidden information, and we can catch that hidden information. We can get we can get uh, acquainted with such type of hidden information if you are having a habit of writing down the assumptions and everything, so that you will come to know what is missing and what is to be found out by using different other sources, like the heat transfer data books mostly. Now, to calculate the rate of heat conduction for a unit length, simply we have to add the two resistances, because both the resistances are in series, and delta T upon the total thermal resistance will give you the value of QR. So, I am just putting the values in this equation. Now, length of the pipe is not known to us, so we can just calculate the length, the rate of heat transfer per unit length. So, I am taking this L out and taking on it on the left hand side. The equations are modified accordingly. Now, just put the values and get the answer, and the answer is 680 watt per meter. So this is very simple calculation. Now, in order to calculate the temperature of interface, that is in between the steel layer and the asbestos layer, let us call that temperature as TA. This is how the TA is going to be there in the resistance circuit. It is in between. Now you can use this resistance or this resistance depending upon your understanding. You can take TA minus T2 divided by this is equal to Q, or T1 minus TA divided by this is equal to Q, because the rate of heat transfer through both the resistances is same. It is up to you for which resistance you want to use. So I'm just using the first one, the steel resistance T1 minus TA, and I'm just putting the values here. QR upon L is already known to me, so I'm just using that QR minus L at 660 and putting all the values, and the only unknown is TA, and TA was calculated and it was found to be 595.8 degree Celsius, which is quite high, because the thermal conductivity of the see only 5 degrees Celsius, or rather 4 degrees Celsius drop is there from 600. It has dropped to 595.8 because thermal conductivity of steel is quite high. It is around 19 watt per meter square Kelvin, and that's why, and the thickness is very small. Okay, because of these two aspects, the temperature drop is in the steel is limited. So this can be our comment on this results. Let's go for the third problem. It is from spherical. A spherical thin-walled metallic container is used to store liquid nitrogen at 80 K. Note the temperature, 80 K. If you convert it into degree Celsius, you will get negative, because it is K, Kelvin. 1 Kelvin or 1 degree Celsius is equal to 273 K. Remember that. So the container has a diameter of 0.5 meter, so quite big, and it's covered with evacuated. Now note these things, very important. Evacuated reflective insulation. It is composed of silica powder. So the powder form insulation is there, which is evacuated completely. The insulation is 25 millimeter thick, and its outer surface is exposed to ambient air at 300 K. Sorry, 310 K, means almost 37 degrees Celsius, normal atmospheric temperature. The convection coefficient is 20, and the latent heat of vaporization and the density of the liquid nitrogen are 2 into 10 to the power 5 joules per kilogram Kelvin. This is the latent heat of vaporization, and density of liquid nitrogen is 804 kilogram per meter. It's liquid, it's not nitrogen gas, so that's why the density is quite high. It's almost in comparison with the water. And respectively, K is evaluated K is evaluated K of evacuated silica powder, that is conductivity of evacuated silica powder is very small, as it is supposed to uh, provide more resistance for the heat to flow. It is the thermal conductivity of the material is very small. You can see 0.0017 meter per meter square. What is the rate of heat transfer to the liquid nitrogen? So in this case, from 10K to this 80K, how much it will flow, that you have to calculate, and what is the rate of liquid boil off. Pause and try to solve. Now I'd like to give you the solution. Now how many resistances are there? From 80K there is the container. Now we are not having any dimensions of the container, only outside diameter of the container is given, so we can ignore the thin walled container directly because no information is available. So thin wall metallic container, whatever thin wall is there, we can ignore the resistance of that thin wall and we can consider directly the outside surface of the thin wall, outside surface of that container, and at the diameter of that is 0.5 meter. So from this 0.5 meter, then the covered, it is covered with 25 millimeter thick, what you call insulation. So at the temperature, at the radius of point, at the sorry, at the diameter of 0.5 meter, let us assume that the temperature is 80K, and from this 80K, there is first resistance is offered by the insulation, and the second resistance will be offered by the heat transfer by convection. So there are two resistances in series once again. One is offered by the insulation, the other one is offered by the environment in the form of convective resistance. So if you draw it, we have to find out the rate of heat transfer and the mass of nitrogen rate boil off. These are our assumptions. Steady state, one dimensional heat flow, negligible resistance through the container, already I told you, because of the thin walled metallic container, and constant properties, no radiation. So with these assumptions we can draw the circuit like this. This is the container, we are ignoring the diameter and all these things. So directly we have got the container outer surface temperature is 80K and the environment temperature is 310K. Heat transfer coefficient is 20, and this thin wall spherical container whose inner radius, outer radius of course, is to be taken as 0.25 meter, and the insulation outside surface R2 is 0.275 meter. So if you add all these things, you can have two resistances in series in between temperature T infinity 1, which is 80K, to T infinity 2, that is 300K. One is offered by the insulation, the other one is offered by the convection. So with this data, where the conduction resistance is for a spherical wall, we know that it is 1 upon R1 minus 1 upon R2 divided by 4 pi K. So, and the convection resistance can be calculated by 1 upon HA as usual. 1 upon H A is 4 pi R2 square. Area of a sphere, surface area of a sphere, 4 pi R2 square, outside area. Okay, because convection is taking place at this outer side surface, that's why R2. Now the rate of heat transfer is then of course T infinity 1 minus T infinity 2, total temperature difference, divided by the addition of the two resistances. So if you put the values in these equations, you can calculate the rate of heat transfer equal to 13.47 watt. Very small rate of heat transfer. You can see because of the very low thermal conductivity of the insulation, there is a very large reduction in the rate of heat flow, and it is only 13.47 watt, which is very small. Now let us find out whether really it is small. Let us do it. Now, what we are interested in finding out how much liquid is boiled off. Now, how to calculate this? We in the previous slide we got around 14 watt of energy is coming into the system, and what will happen because of this? Whatever liquid nitrogen is there, because of the addition of the small amount of heat, 13 point something, it is going to get boiled off. It will get evaporated. Okay, and this rate of evaporation we have to calculate. So we can do it by using the energy balance, and the energy balance is very simple. First law of thermodynamics: energy coming in minus energy going out is equal to 0. What is E in this case? Where E in is equal to the rate of heat transfer. What is coming in? The rate of heat transfer. What is going out? Where it is going? It is going for the evaporation of the nitrogen. Now, how we can write down the evaporation? We can write out in terms of mass into the latent heat of vaporization. We already are having this value of M, sorry, HFG, and we are interested in finding out what is the M. What is the relation? Now, if you put this En in I out in this equation, what will you get? Hence, Q minus M dot HFG is equal to 0, or Q is equal to Q is equal to M dot into HFG, and M dot is equal to then Q upon HFG, and can be calculated as 13.47 divided by HFG is already given 2 into 10 to the power 5, and you can see that 6.74 into 10 to the power minus 5, very small amount of liquid nitrogen is getting boiled off. But really whether, once again I'm telling, whether really it is very small, let us find it out. So let us do it for a day. So mass flow rate is 6.74 into 10 to the power minus 5 into 36 seconds, 3600 seconds per hour, 24 hours. So in a day, 5.82 kilograms of liquid nitrogen is going to get boiled off. Now you can imagine. It was appearing to very small, 6.74 into 10 to the power minus 5. But in a day, it is going to get 5.82 kilograms per day. Now it is looking to be a good figure. Now on the volumetric basis, normally because for liquids we are specifying volumes, we are not specifying the masses. So if you calculate a volume, because we are having the density, so volume is mass upon density. So we can calculate that density, and it was found to be 7.24 liters per day. 7.24 liters per day. Now what is the total volume? If you calculate the total volume of the container, it is 65 liters, and on a daily basis 7.25 liters is going to get evaporated. It means that 11% of the capacity of that liquid nitrogen is getting evaporated daily. It means that even if you are providing such a very low conductivity insulation, it is not sufficient. It is going to prevent, means maybe the total evaporation may need around 9 days. In the 9 days, the liquid nitrogen is going to be evaporated, which is not at all expected. So within 9 days, either we have to consume it, or we have to change the insulation in order to get better results from this. So that is how this type of simple calculation can help us in practice also. So this was about the third problem. In this lecture, we have dealt with the composite wall problem, the solution of composite cylinder problem, and composite sphere problem. Okay, thank you very much.